In this chapter, we're going to look at acids and bases. Now, we've seen acids and bases already in lab. We've used them several times at this point. Things like nitric acid or hydrochloric acid, or bases like sodium hydroxide or ammonia. We've also seen how to name acids and bases, which are ionic compounds, back in chapters 5 and 6, where we looked at nomenclature. So in this chapter, we're going to go into a little bit more detail. We're going to look at how to define acids and bases. What is it that makes something acidic or basic, or what do we mean by that? And then we'll just look at what acids and bases do. So I've pointed out that we've used acids and bases quite a bit in lab already. Acids are very useful compounds. They're just very capable of carrying out a whole bunch of reactions, as you've already seen in lab. In fact, sulfuric acid is one of the largest produced fine chemicals in the country. All right. Now, we're going to notice that acids have a lot of properties in common. All right. So whenever we tend to taste something sour, that sour taste is usually from something that's acidic. All right, we've seen reactions involving acids in lab, but even in just general biology, for digestion, you need hydrochloric acid in your stomach to help digest your food. Okay, so what is it that makes things acids? Well, we're going to go into more detail on this in a few slides, but for now, you'll notice that all of the acids we've looked at so far have had hydrogen in them, right? So things like HCl or HNO3 or H2SO4. Notice that they start with a hydrogen. And the reason for this is that these acids act as acids because when they dissolve in water, they give off hydrogen ions. Okay, so even though they are compounds made up of just covalent or just non-metals, and therefore you think they'd be strictly covalent, when they dissolve in water, they actually behave slightly ionically. Okay, and again, we'll go into more detail into this later on in this chapter, because there's a little bit of nuance to that. All right, so it's these hydrogen ions that give that sour taste when you taste something acidic. Okay, so for example, vinegar, which is acetic acid, or most citric fruits like lemons have citric acid. These have that tart, sour flavor due to these acids present. Now, we've seen before that we can split acids into two main types, or at least two that we've seen already. I'll introduce another one in this chapter as well. But we've seen binary acids, which are made up of a hydrogen and one other non-metallic element. And then we've also seen oxyacids or oxoacids, where we have hydrogen ions balancing out some negatively charged polyatomic ion, usually something containing oxygen, like nitrate or sulfate or phosphate and so on. Now, there's a third type of third type of acid, and that's organic acids, or also known as carboxylic acids. These are known as carboxylic acids because they have a carboxyl group. Okay, that's a carbon double bonded to an oxygen, and with an OH group, and that hydrogen that's attached to that oxygen is particularly acidic. You wind up having that hydrogen break off as a hydrogen ion relatively easily. Okay, so again, these are organic acids because they are primarily carbon, hydrogen, and oxygen based, and something being comprised primarily of carbon and hydrogen is by definition what makes something organic. Okay, so acetic acid is an example of a weak acid you're probably going to see quite a bit. That's an example of a carboxylic acid. All right, so the formula of acetic acid is CH3COOH, or you might see it written out as HC2H3O2. The key thing is that this is the actual structure. All right, it's got this carbon with 3 hydrogens attached to it. That's what we call a methyl group. These hydrogens actually don't break off. These carbon-hydrogen bonds are relatively difficult to break, so these hydrogens here are not acidic. It's only this hydrogen that's attached to this oxygen that allows that hydrogen to break off as an ion pretty easily and turn this into an acid. All right, so you can actually get a lot of different acids by just swapping out this alkyl group over here. Don't worry about what an alkyl group is. It's basically something, a attachment that's made up of carbon and hydrogen. If you go on to organic chemistry, you'd worry a little bit more about that. But the key thing is that as long as you have this carboxylic acid group, you have a carboxylic acid. So that's why we tend to write out acetic acid oftentimes as CH3COOH, because this combination here makes it really easy to recognize the presence of this functional group. Okay, so let's do a little review here. We talked about this back in chapter 6, but we can name binary acids fairly easily. We take the non-metal that's not hydrogen, and we use that first syllable as the kind of root of the name. Now we add the prefix hydro and the suffix ic acid to it, but that's how we get the name of the acid. So for example, HCl. All right, now Cl is chlorine, so we take that root word chlor, that first syllable of chlorine, chlor, and we add a hydro before it and an ic acid after it. So it becomes hydrochloric acid. Okay, so here we have HI, where I is iodine, right? So you take the iode, which is kind of the first syllable and a half, that root word of iodine, and you have hydroiodic acid. Okay, so think about how you would name HBr. Okay, Br is bromine. Okay, so think about that first syllable there, brome, and so it becomes hydrobromic acid. With oxoacids, we've seen that we can take the our name of our polyatomic ion, all right, and that usually gives us a hint about what the root of our acid is going to be. All right. Now, the thing to note with your polyatomic ions, if you have an 8 ending to it, so things like nitrate or sulfate or phosphate and so on, the acid is going to have the suffix ic acid. Okay, so sulfate gives us sulfuric acid, nitrate gives us nitric acid, phosphate gives us phosphoric acid, and so on. Okay, now we've seen before that with these polyatomic ions, if you take away an oxygen from these 8 ending polyatomic ions, the suffix changes into ite. Okay, so if you take away an oxygen from nitrate, it becomes nitrite. If you take away an oxygen from sulfate, the example given here, it becomes sulfite. Okay, notice that the charge remains the same even though you've got one fewer oxygen. All right. So in the case of these ions that end with ite, the acid's going to end with us acid. Okay, so keep that in mind when you look at your ion name. You're going to have the corresponding acid name to line up with that. Okay, so sulfite gives us sulfurous acid, nitrite gives us nitrous acid, and so on. Oh, and by the way, if you want to figure out the number of hydrogens you need, just know that since hydrogen has a +1 charge, you're going to need the same number of hydrogens as the number of negative charges on your ion. Okay, so sulfuric acid has 2 hydrogens, nitric acid has 1 hydrogen, phosphoric acid has 3 hydrogens, and so on. It corresponds to the negative charge on the ion. Okay, so we've talked a lot about acids. What about bases? The most common bases you're going to come across are metal hydroxides. Now, specifically, we use group 1 and group 2 metal hydroxides. If you recall, group 1 metals are known as alkali metals, and group 2 metals are alkaline earth metals. The bases that they form are sometimes called alkalis, and that's why those metals have that name. All right, so typically they're just the metal ion paired up with a hydroxide ion. Hydroxide is OH minus, and it's this hydroxide ion that gives your metal hydroxide its basicity. Again, we'll talk a little bit more about what it means to be basic in a second. But bases tend to have a bitter taste, and again, it's that hydroxide ion that provides that bitter taste. Bases will combine with a lot of organic compounds, especially fatty acids from animal fat, to make soap. So oftentimes, if you touch a strong base, it feels kind of slippery. That's basically your skin turning into soap. That's so. If you do that, if you feel your fingers feeling particularly soapy after touching a strong base, you might want to clean that off in a hurry. Um, yeah, so typically you have a group 1 or group 2 metal hydroxide, and that's how you know that's going to be a base. Another example of a base that you'll come across pretty frequently is ammonia. Ammonia, which is NH3, is a weak base. The reason it's basic is that it will dissolve in water to form ammonium hydroxide, and that's the source of those hydroxide ions that will cause ammonia to act basic. Now, in terms of figuring out the name of a base or its formula, this is really straightforward, right? It's just your general ionic nomenclature. Since your metals are group 1 or group 2 metals, you just have to say the name of that metal followed by hydroxide, because that's the name of the hydroxide ion. You don't have to worry about any numbers, any prefixes, no Roman numerals, nothing like that. It's really straightforward naming. Okay, the only thing to realize when you're looking at the formula of your hydroxide is if you have a group 1 metal like sodium or potassium or lithium and so on, you only need one hydroxide to balance it out, because the +1 charge on your metal ion balances out with the -1 charge on your hydroxide. Now, if you have a group 2 metal like magnesium or calcium and so on, you need 2 hydroxides for that, because those group 2 metals have a 2+ charge. But please note that the name still stays, metal hydroxide. Again, that's because that's how we name ionic compounds like that. Okay, it's still the same rules we learned back in chapter 5. Okay, with ammonia, you might see it written out like this as ammonium hydroxide, but please know that even if you see ammonia, NH3, you should readily recognize that as a weak base. Okay, so I've already given you a hint as to why certain chemicals act as acids or bases, right? We've already talked about how acids have hydrogen ions and bases give off hydroxide ions. This is known as the Arrhenius definition of an acid and a base. There are 2 other definitions. We have 3 total different ways to define what makes an acid acidic and what makes a base basic. The Arrhenius definition is probably the most common one that you may have already come across in other science courses, or just in general, you must have heard it at some point. Okay, that acids have H+, bases have OH-. However, the next definition we're going to look at, the Bronsted-Lowry definition, is probably going to be the more useful one for you in this class and probably future chemistry classes as well. The problem with the Arrhenius model is that it limits us to just your typical acids, your typical metal hydroxides as bases, and how they behave in water. However, acidic and basic behavior is observed in a much wider context. What we do in the Bronsted-Lowry definition is we choose to focus on one piece of the reaction, and that is a hydrogen ion. So in the case of an acid gives away H+. Now, at this point, this is very similar to the Arrhenius definition, where an Arrhenius acid is something that gives off H+ as well. Just for the convenience of saying this out loud, instead of saying the word hydrogen ion, we refer to hydrogen ions as protons. Okay, so we call an acid a proton donor. It's something that gives off a hydrogen ion, which is essentially a proton. All right, if you're having trouble seeing that, remember a hydrogen atom, the most common isotope of hydrogen, the element, it has 1 proton and no neutrons, and it has 1 electron to balance it out. So if your hydrogen atom loses that 1 electron to become H+, all that's left is a proton. Okay, hence the name. Now, here's where the Bronsted-Lowry model differs from the Arrhenius model. In the Arrhenius definition, a base is something that gives off OH minus. The Bronsted-Lowry definition doesn't require this. In the Bronsted-Lowry definition, remember, we're looking at where that H plus ion is going. Where's that proton going in our reaction? So if in the Bronsted-Lowry definition, an acid is a proton donor, well, something's going to take that proton, right? So a base is a proton acceptor. It's the thing that picks up the H plus from the acid. So in other words, according to Bronsted-Lowry, in order for an acid to act as an acid or a base to act as a base, they need to work together. You always have acid-base reactions, okay, where an acid and a base will react with each other. Okay, one of them will give off a proton, the other one will take in that proton. So let's see an example of how that works. Now, a quick note here about protons. Protons themselves aren't actually very stable. So we actually do see a lot of these reactions happening in water, and what happens there is that proton basically attaches itself to a water molecule. When it does this, it forms what we call a hydronium ion, H3O+. Okay, this is the stable way that a proton exists in water. So even though I'll refer to protons or hydrogen ions, I'll even just write it out as H+, as you can see in this top reaction over here, that's really the lazy way to write it. The real way is like this. So when we see hydrogen chloride gas, those hydrogen chloride molecules dissolving in water and splitting up into hydrogen ions and chloride ions. Okay, and again, it's these hydrogen ions that make it an acid, according to Arrhenius. What's really happening is our hydrogen chloride molecules are reacting with water molecules. They're transferring that proton and becoming chloride. And in losing that proton or giving it away, HCl is acting as an acid here. But now, look at this interaction. Notice that while the HCl is giving away a proton, it has to give it away to something. The water is accepting the proton to form hydronium. Now, that means in this situation, water is actually acting as a base. So that's something that you want to keep in mind when you are looking at how we define our acids and bases. You have to consider that water can also act as a base. Now, does that mean that water is always a base? No, water is actually what we call amphoteric. It can act as an acid or a base depending on the situation. Don't worry about that word amphoteric. I'll come back to that later on with a spelling for you. But for now, understand that water can act as, it's acting as a base here, but that doesn't mean it's always a base. So if you can't memorize what water is going to be, well, you then have to see where's that hydrogen going. So here's a generic example. So we have some generic acid, HA, and it's reacting with water, and it's forming hydronium, H3O+, and A-. So what's going on here? Look at HA. What is it becoming? It's becoming A-, right? That's how it's acting as an acid. It has to give away that hydrogen ion. It's got to give away H+. So you can tell that it's done that because it's missing that hydrogen. It's just the A. And since that hydrogen left with a positive charge, what's left behind is negatively charged. Okay? We call this the conjugate base of our acid. Okay, the reason for that name is that means in the reverse reaction, A- could pick up an H+ to go back to being the acid. Okay, it may or may not do this. We'll talk about whether or not this happens when we look at strong versus weak acids. But just the fact that it could theoretically do that gives it that name, conjugate base. Now look at water. Water becomes hydronium. Okay. So how is hydronium different from our water? Notice that it has an extra hydrogen and has gone from being neutral to being positively charged. So how's it changed? It's gained an H+. It's got an extra hydrogen and an extra positive charge, which means it gained a H+. It gained a proton. So that means that the water is a base, and hydronium is its conjugate acid. In the reverse reaction, our hydronium would lose a proton to go back to being water, so it would act as an acid in that reverse reaction. So we call hydronium that conjugate acid. Okay, so please note that the conjugates, our conjugate acid, our conjugate base, are always on the product side of the equation. They're always on the right-hand side. Okay, our acid and our base are always on the reactant side, on the left-hand side. Okay, and there you have it. So you'll always have an acid and a base, and you'll always have a conjugate acid and a conjugate base when you see these reactions. Okay, let's try an example with actual chemicals. Now, this is actually the example you saw earlier, but let's see if we can look at let's pay attention to how these chemicals are changing. So we have HCl over here, and it's becoming Cl minus. Okay, and a good way to pay attention to this is to look for those non-hydrogen elements and see where they're repeated. So you can see that we have chlorine in HCl, and we have chlorine in our chloride ion. So how is Cl minus different from HCl? Well, in order from HCl to go to Cl minus, it's got to lose a hydrogen, and that hydrogen must be positively charged to leave behind this negative charge. So our HCl donates a proton, loses a proton to become chloride, which means HCl is our acid. Now look at water. Water gains an H plus to form hydronium, so water must be our base. And of course, hydronium is the conjugate acid of our water, and chloride is the conjugate base of our acid. By the way, these are known as conjugate acid-base pairs. So HCl and Cl minus are a conjugate acid-base pair. The only thing that differs between them is that proton. Okay, so keep that in mind. That that's basically how you can recognize a conjugate acid-base pair. They are essentially the same molecule, but one is different by an H plus. Okay, they're just separated by one H plus ion. So water and hydronium is another example of a conjugate acid-base pair. All right, let's practice this again. Let's try another example here with ammonia and water to form ammonium and hydroxide. Feel free to pause this video and see if you can identify the acid, the base, the conjugate acid and conjugate base in this equation. Okay, so if you're back now, let's look at ammonia and see what it becomes. So again, if you're having trouble tracking this, notice that we have a nitrogen in ammonia. So I would look at the molecule that has nitrogen here as well. That's this ammonium ion. So how is NH4 plus different from NH3? Well, we've got an extra hydrogen. We've got 4 hydrogens instead of 3, and we've got a positive charge instead of being neutral. So that tells you that we had to gain an H plus to form this molecule, which tells us that ammonia must be a proton acceptor and therefore a base. Okay. Now, by the way, if you figured out one of these, you can kind of figure out all the rest. If this is your base, the other reactant must be your acid, and that means these two are conjugates. If this was your base, the molecule it becomes must be your conjugate acid, right? Because they form a conjugate acid-base pair. And likewise, if this is your conjugate acid, the other product must be your conjugate base. Okay, but of course you can check your work, right? If water is acting as an acid in this situation, it must lose an H plus. It must donate its H plus to form its conjugate base hydroxide, which makes sense. Hydroxide has one fewer hydrogen, and it's missing a positive charge. That's why it's negatively charged. That tells you that it must be the conjugate base of water, which must be the acid. Okay. So something to keep in mind, again, for these conjugate acid-base pairs. And again, always remember your acid and base are on the reactant side. Your conjugates are always on your product side. Okay, let's practice this. Here are some examples of, just 2 different molecules or ions. Ask yourself, are these conjugate acid-base pairs? Okay. So that first one should be pretty straightforward, right? You remember, I think I even referred to this as an example. Water and hydronium are a conjugate acid-base pair. And you can tell that because, again, they're different only by one H plus ion. Okay, so if you add a if you add a hydrogen ion to water, it forms hydronium. Okay, so that's the difference. This has an extra H plus. Okay, so go ahead and look through all these others and see if they're also conjugate acid-base pairs. Okay, so I think you probably saw me accidentally give away the answer a second ago, but you probably quickly find out these two are not conjugate acid-base pairs. Okay, the reason for that is they're not related at all, right? Nitrate or nitric acid has a nitrogen in it. The rest of the molecules should be present in your conjugate acid or base. So there's no nitrogen here, so that should give that away. But quite frankly, if you just pick one of these and add or subtract an H plus from it, you should get the other one, and that's just not the case. If we add a hydrogen ion to OH minus, we would get water. If we took away a hydrogen ion, an H plus from that, we would get an oxide ion, and neither of them is nitric acid. Okay, nitric acid here has a conjugate base that's NO3 minus, but again, that's not what's shown over here. Okay, now this one is a tricky one. All right, now you might look at this and say, oh, these are definitely related, right? If I lose 2 protons, my sulfuric acid will form sulfate. But that's the trick. There are 2 protons you've got to lose. A conjugate acid-base pair are related by 1 proton. Okay, so they're not paired because there are 2 protons involved here. Now, what this means is that they actually have a conjugate in common. The conjugate base of sulfuric acid is HSO4 minus, or hydrogen sulfate. Hydrogen sulfate can lose that 2nd proton, and so when hydrogen sulfate, even though it's a conjugate base of sulfuric acid, it itself can also act as an acid, and when it does, sulfate is its conjugate base. All right, so even though this is not a conjugate acid-base pair, they have HSO4 minus as their mutual conjugate. Okay, so that was a tricky one. All right, the last one hopefully should be relatively straightforward. Okay, hopefully looking at it, you probably realize that the difference between these two is just 1 hydrogen ion, and therefore, yes, they are a conjugate acid-base pair. Okay. So, earlier, I talked a little bit about whether these reactions are, go in one direction or are reversible. And I kind of alluded to that and said that that would relate to the strength of an acid. And that's something you've heard before. You've heard of strong acids or weak acids, or strong bases or weak bases. And basically, what does that mean? What does it mean to be a strong acid versus a weak acid? Well, the distinction is actually the same difference that we see with electrolytes. A strong acid is a strong electrolyte. A weak acid is a weak electrolyte. All right. Now, what is it that makes a strong electrolyte a strong electrolyte? Remember, a strong electrolyte is something that dissolves in water and completely splits up into its ions. It completely dissociates into its ions. So for example, here our generic acid HA will dissolve in water and it'll form hydronium and it'll form A minus, its conjugate base. Now notice that we're using a regular arrow here, which shows us that this reaction is going to completion. All of our HA is forming hydronium and conjugate base. Okay, so that tells us that we have a strong acid because that's a strong electrolyte. Right? A strong electrolyte completely breaks up into its ions, and that's shown by that regular forward arrow. What about weak acids then? Well, remember, with a weak electrolyte, instead of seeing this regular arrow, we see a reversible arrow or an equilibrium arrow. And the reason for that is because the reverse reaction predominates. We have some of our acid forming ions, but not all of it does. A lot of that reverse reaction takes over, and we have these molecules mostly staying intact. Okay, our hydronium ions and conjugate base will go back to forming these whole molecules. Okay, and again, that's by definition what a weak electrolyte is. It's something that doesn't completely form these ions. It stays mostly intact, but it forms some ions. Okay, so I've shown only this reverse arrow here, but really we can show this with your typical typical equilibrium arrows. Remember, you normally see it kind of like drawn like that, okay, to show that equilibrium or that reversible reaction. Okay, so if in the last chapter when we looked at reversible reactions, we saw that we can figure out how do we define an equilibrium? How do we understand what's our ratio of reactants to products? We could basically quantify that using what we called an equilibrium constant. So we'd set up an equilibrium expression, Kc, and it would have our concentration of products over our concentration of reactants. And based on the value of Kc, we could tell whether our equilibrium preferred our products or reactants. Okay, and we're going to do the same thing with acids here. Okay, if we have mostly products, what's going to happen to the value of our equilibrium constant? Well, it would be a large number. So that tells you that you would have a strong acid. Okay, and vice versa for a weak acid. If you have a weak acid, you're going to have a very low equilibrium constant. So what we're going to do, though, is we use a special equilibrium constant. We call it Ka. The A, as you've probably guessed, stands for acid. So this is what we call the acid dissociation constant. So if we describe the equilibrium of an acid, and we can quantify that equilibrium using Ka, the value of Ka will tell us just how weak is our weak acid. All right. Now you might not see Kas for strong acids very much because they aren't really described as equilibria, but technically you can. You'll just get a very, very large number for Ka. So that's why you typically don't bother treating it as an equilibrium at all. It's pretty much shifted to one side. But so you'll see this mostly for weak acids. Now let's look at a generic example here. We have Ha. Dissolving in water to form hydronium and the conjugate base A-. So let's write out an equilibrium expression for that. Our products, hydronium and A- will go on our numerator, and our reactants, Ha and water, should go on our denominator. I wonder why water's missing. Okay, if you were wondering about that, since the slide opened up, I'll ask you to think about the state symbols of these chemicals. Ha would be aqueous, as would hydronium and A-. Water, remember, is a liquid, and solids and liquids do not show up in your equilibrium expression because they don't have a changing concentration. All right, so that's why water doesn't show up. It doesn't technically have a concentration. So you would basically just plug in these numbers, these concentrations, and you could calculate your value of Ka. Or alternatively, if you are given the value of Ka, it tells you how much of these ions, how many of these ions do we get from our weak acid. And so the smaller the value of Ka, that tells us the weaker this acid is, because we're going to have less and less of this product, and your acid mostly stays intact. So let's look at an example here. Here's formic acid. All right, the root word of that former comes from the Latin word for ant. So fire ants actually use formic acid in their venom, in their stings. So basically, formic acid, it's an organic acid, a carboxylic acid that dissociates in water here to form hydronium and formate. Now, it's a weak acid, so this is an equilibrium. If you calculated the value of Ka, you would find that it is 1.8 times 10 to the negative 4. Now, that's a very small number. If you recall from the previous chapter, anything lower than 1 is probably, you could treat that as being reactant favored, right? And in this case, we have 0.00018. That's a very small number. So that tells us we have very little of these products, and mostly this reactant is present. Okay, so that tells us that this is a weak acid. But this again is how we would set up the equilibrium expression. And it's the same thing we learned in the last chapter. You have your products, hydronium and this conjugate base formate, and those are your go in the numerator of your equilibrium expression. And on the denominator we have our reactant. Okay, that goes over here. And of course, we leave out water because water is not, well, water is a liquid, right? So it doesn't show up. Okay, so that's basically, how you can look at a weak acid and see how weak it is. You could compare weak acids by comparing their Ka values. All right, so the smaller the value of Ka, the weaker your acid is. Okay, so for example, phosphoric acid is a weak acid, but it's yet stronger an acid than, let's say, acetic acid. Okay, so anyway, that's my point here. You could use these Ka values to quantify just how weak these acids are. Right. By the way, if you wanted an example of a Ka value for a strong acid and why we don't really treat them as equilibria or even bother calculating out Ka values, the Ka value for something like hydrochloric acid is somewhere in the ballpark of 10 to the power of 7. Right, so that's like that's 10 million, right, as your Ka value. For sulfuric acid is 10 to the power of 9, right? That's a billion, basically. Okay, so here's another example. So here we have hydrogen sulfide, H2S. So that will act as a weak acid. Okay, so even without the Ka value, let's see how to write out the Ka expression. So remember, you want to first write out the equilibrium that it's in. Acids will always react with water to form hydronium and a conjugate base. Okay, we saw that earlier in this chapter. So your reactants are your acid and water, and your products are hydronium, H3O+, and the conjugate base. Now remember, your conjugate base is just your acid missing an H+. So however many hydrogens it has, subtract one of them. So instead of 2 hydrogens, we only have 1. Whatever your charge is, subtract a positive charge because it's losing an H+. So it's neutral here. So if you take away a positive charge, you're left with a negative charge. And that's why its conjugate has a negative charge. All right. Once you have the equilibrium written out, the equation, you can write out an equilibrium expression. So these two products go on the numerator. Their concentrations go on the numerator. And the denominator has the intact acid, H2S here. Okay, and of course that's equal to Ka. So again, please note it's Ka, not Kc. So why don't we practice this? So go ahead and write out the equilibrium expression for hypochlorous acid. Okay, so hypochlorous acid is HClO. I recommend starting off by writing out an equilibrium, like an actual equation for it. So show the reaction of hypochlorous acid with water to form hydronium and perchlorate, or chlorite rather. And and then write out your equilibrium expression. Okay, so hopefully you got this written up. So here's our hypochlorous acid reacting with water. Here's hydronium, H3O+. And to get the formula of hypochlorite, we would just take away an H+. So we lose this one hydrogen, so left with ClO. And because that hydrogen takes away a positive charge with it, the resulting ion would have a negative charge. Okay, and of course these two ions then would be on your numerator, and your denominator would be this. It would be your hypochlorous acid, just intact. Okay. By the way, this hypochlorite ion is the active ingredient in bleach, in case you were curious. So sodium hypochlorite is the resulting salt from this. Okay. Now that, by the way, is why bleach is basic. This is a conjugate base of a weak acid, which means that it's actually a decent base. But I'm getting a little ahead of myself. We'll talk about acidic and basic salts towards the end of this chapter. Okay, so most of the examples of acids we've seen so far are what we call monoprotic acids. They give off only one hydrogen. All right, so things like nitric acid, which is HNO3, hydrochloric acid, which is HCl, they have only one hydrogen. You can have what's called a polyprotic acid. Polyprotic acids, as the name suggests, have many protons. They have many hydrogen ions that they can give off. Okay, so you can usually tell this in their formula. So phosphoric acid is triprotic. It has 3 hydrogens. Carbonic acid is diprotic. It's got 2 hydrogens. Okay, so again, these are polyprotic acids. They have many protons, many H+ ions they can give off. Now, typically, these polyprotic acids are weak acids. If you go back to that slide where I list out the Ka values for various weak acids, you'll notice that a lot of them are polyprotic acids. Okay, now again, that doesn't mean that every weak acid is a polyprotic acid. Acetic acid is a monoprotic acid, and that's a weak acid. Or nitrous acid is a monoprotic acid, and that's a weak acid. But that being said, pretty much every polyprotic acid you're going to come across will be a weak acid. Okay, so not all. You could generally have the rule of thumb that all polyprotic acids are weak acids. Not all weak acids are polyprotic acids. However, there's one exception to that rule that all polyprotic acids are weak, and that is sulfuric acid. Sulfuric acid is diprotic. It's got 2 hydrogens. All right, it's H2SO4. However, it is actually a strong acid. Okay, we'll see how in an example. Let's contrast it with another polyprotic acid. So carbonic acid, we've seen, is diprotic. So it will lose its first proton, its first H+. Accordingly, it forms, your H2CO3, your carbonic acid, will react with water to form hydronium and bicarbonate. All right, now bicarbonate is just carbonic acid missing a hydrogen ion. So it's HCO3 with a negative charge. Okay, so here we have this conjugate base, and of course it can do that reverse reaction to go back to forming carbonic acid. That's what makes it a conjugate base. However, notice that it still has that other hydrogen. So it can itself go on to form to act as an acid. So it will react with another equivalent of water and form another hydronium and form carbonate, which is its conjugate base. Okay, so notice that our bicarbonate ion here, HCO3-, can either act as a base to go back to being carbonic acid, or it can act as an acid to form carbonate. Okay, so carbonic acid here is what we call amphoteric. Okay, so like water, it can also act as either an acid or a base depending on the situation. Now, here's why sulfuric acid is different. Sulfuric acid will also have a conjugate that's HSO4- that you'll see in 2 reactions. You can see that sulfuric acid will form HSO4-. HSO4- can then, of course, act as an acid and form sulfate. However, notice the difference in the arrows here. This second reaction is a reversible reaction. It's an equilibrium. Sulfate and hydrogen sulfate exist in equilibrium. Okay, you'll have some hydrogen sulfate going on to sulfate, but you'll have some sulfate going back into hydrogen sulfate. Okay, but look at this first reaction here. While sulfuric acid will form hydrogen sulfate is actually pretty lousy at being a conjugate base. It does not do the reverse reaction. All right, it does not go back into forming sulfuric acid, so this is an irreversible reaction. It just goes in one direction, and this is the reason that sulfuric acid is a strong acid. Notice that over here, H2SO4 is acting as a strong electrolyte. It's completely breaking up into our hydronium and conjugate base. All right, this complete dissociation is what makes sulfuric acid a strong acid. So, that being said, how do we remember which of our acids are strong acids, which of them are weak acids? Which of our bases are strong bases, which ones are weak bases? Unfortunately, you're going to have to memorize this. All right. That being said, I've made this table here to kind of break it down to make it a little bit easier to keep in mind. All right. So, when it comes to strong acids, the only strong acids you're really ever going to see are nitric acid, sulfuric acid, hydrochloric acid, and perchloric acid. Okay, HCl4. To be honest with you, the most common you'll see are nitric acid, sulfuric acid, and HCl. Typically one of these 3. The other acids in that hydrohalic family, so HBr and HI, those are also strong acids, but one notable exception is HF. Fluorine is so electronegative, it prefers to hold on to that hydrogen and not allow it to behave as an acid. So HF is a notable exception to that family of HCl. Okay, so you have to remember that HBr and HI are also strong acids. Okay, but like I said, typically the most common ones you'll see are nitric acid, sulfuric acid, and hydrochloric acid. You can pretty much assume that any other acid you're going to come across is going to be a weak acid. If you're not told otherwise, just assume that if it's not nitric acid, sulfuric acid, or hydrochloric acid, or hypochlorous acid, hypochloric acid, sorry. Just assume that it's a weak acid. Oh, sorry, I forgot to mention here. Chloric acid, HClO3, that's also a strong acid. But you can assume that chlorous acid, which is HClO2, and hypochlorous acid, HClO, those are going to be weak acids. What about bases? Bases are even easier to remember. Anytime you see a group 1 or group 2 metal hydroxide, just assume it's a strong base. So that includes, things like sodium hydroxide, potassium hydroxide, calcium hydroxide. So anytime you see a group 1 or group 2 metal followed by OH in some combination, you can assume that that's a strong base. The only weak base you guys are ever going to really come across in this class is pretty much just ammonia. All right, so ammonia or its its dissolved form of ammonium hydroxide. That's pretty much the only weak base that you guys are going to see. There are other weak bases out there, of course. A common one you'll see in organic chemistry is pyridine. A lot of amines, which are kind of organic derivatives of ammonia, are also weak bases. But you don't come across them very often in Chem 103, so don't stress too much about them. Okay, so let's practice this. Here are some examples of some acids and bases. Ask yourself, is this an acid or base, and accordingly, is it strong or weak? Okay, so if you're having trouble seeing this, flip back to that previous slide. But take a second, pause this, and see if you can identify these as strong acids, strong bases, weak acids, or weak bases. Okay, and so here are the answers. So you can see we've got HBr. It's in the same family as HCl. It's going to be a strong acid. You can see that here we have an H followed by NO2. So it's going to be an acid. But notice that it's not nitric acid, hydrochloric acid, or any of those other acids that we described as being strong. This one's a little tricky. You might look at this and say like, oh, it's almost like nitric acid. This is nitrous acid, HNO2. But since it's not nitric acid, it is a weak acid. You can just assume it's a weak acid. NaOH. Again, Na, that's sodium. It's a group 1 metal. And OH, that's hydroxide. That immediately tells you this is going to be a base. But more importantly, it's a strong base. H2SO4, you should recognize that as sulfuric acid and immediately see that's a strong acid. It's one of the few strong acids you need to memorize. And then, of course, NH3, that's the only weak base you need to memorize, so you should immediately recognize that as a weak base. Okay, so let's talk about water in general. I've mentioned earlier that something that acts as an acid or a base, depending on the situation, is amphoteric, and here's that spelling finally. So amphoteric means it can act as an acid or a base depending on the situation, and water is probably the most famous of these amphoteric substances. Now, the cool thing about water being amphoteric is that it can act as an acid or a base with itself, right? So even if you don't have an acid or a base present to interact with the water, water will just, do an acid-base reaction by itself. This is known as the autoionization of water. So we can see that here, where two water molecules come together, one of them picks up a proton to form hydronium. The other one, basically loses a proton to form hydroxide. Okay, So in this example here, this water molecule is acting as the acid. It's donating a proton to this water molecule over here. And so that becomes hydronium, which is the conjugate acid. And this one becomes hydroxide, which is the conjugate base, right? The one that lost a proton forms its conjugate base. Okay, and again, notice that we have ions here. Right, so that's why it's called the autoionization of water ionizing itself. Now, I've shown this with a regular forward arrow, but that's kind of generous. This is actually a very weak reversible reaction. All right, so you'll only have a small percentage of these conjugates. Okay, water mostly stays water molecules. Okay, so how small are we talking about here, right? We're talking about 1 times 10 to the power of -7 molar. So that's 0.0000001 molar concentration of either hydronium or hydroxide. Okay, so we're dealing with a very low concentration here at room temperature. Okay, so how do we calculate the Ka for water then, right? Well, again, your products here are hydronium and hydroxide. Since your reactants are both water, they don't show up in your equilibrium expression. So we have a special equilibrium constant here, and we call it Kw, the ion product constant of water. And in the case, so if you're at room temperature, where each of these numbers is 1 times 10 to the -7, when you multiply them together, you get 1 times 10 to the -14. Okay, and that's the value of Kw. Now, here's the really cool thing about this. This value of Kw, this relationship between hydronium and hydroxide ions, holds true even when you don't have pure water. If you have an acid or a base present, this Kw constant will still be 1 times 10 to the power of -14. Okay, now you're probably asking yourself, how does that happen? Well, these two concentrations will change to compensate, or to sort of balance out whether you have excess hydronium or hydroxide from your acid or base, respectively. It's kind of like Le Chatelier's principle in play. Okay, so if you have an acid present, and an acid increases the concentration of H+, what will happen is the concentration of OH- will decrease in that equilibrium that we see from the autoionization of water. And in doing so, it'll keep that Kw at 1 times 10 to the -14. Likewise, if you add a strong base, your concentration of hydroxide will go up, your concentration of H+ will decrease to compensate for it, and your Kw will still stay 1 times 10 to the -14. So, what does it mean for a solution to be acidic or basic? Well, remember, in that Arrhenius definition, an acid is one that has a lot of H+ floating around. So if your H+ concentration is greater than your OH- concentration, that tells you that you have an acidic solution. Likewise, if your OH- concentration is greater than your H+ concentration, you have a basic solution. Okay, and again, please note I'm using the lazy way of writing out H+ instead of hydronium for all of these. So just a little definition here. A solution is neutral when H+ and OH- are equal. If you have more H+, it's acidic. If you have more OH-, it's basic. And in all of these cases, the key thing to remember is that whatever your H+ concentration, whatever your OH- concentration, the two of them multiplied by each other will always give you Kw, which is 1 times 10 to the -14. Okay, so that's a great way to calculate one from the other, because you know that the two of them multiplied together will always give you that number. So let's try an example where we do a calculation involving that. What is the H+ concentration of a solution which has a hydroxide ion concentration of 2 times 10 to the -2 molar? Okay, you could see that written out as 0.02. Okay, that's what that number would be in decimal form. But the key thing here is that we want to figure out what's that concentration of H+. How do we calculate that from that OH- concentration? Okay, now there's a follow-up question to this. Is this solution acidic, basic, or neutral? Let's first figure out that H plus concentration, because that'll help us answer that second question. So, to do this, you have to remember that your Kw is your concentration of H plus times your concentration of O minus, and it's going to be 1 times 10 to the negative 14. This is effectively the formula that you're using here. Okay, and typically you're provided with this. You don't really have to memorize this. Okay, now, how do we figure out what our H plus concentration is? We know our OH minus concentration. How do we get H plus by itself? Well, there's nothing in between these two terms, so we know that they're effectively being multiplied by each other. So what's the opposite of multiplication? Well, we would divide by our OH minus concentration. So if we do that, okay, and we plug in that number, our H plus concentration is 1 times 10 to the negative 14 divided by 2 times 10 to the negative 2. Okay, I do recommend practicing this on your calculator. I find that students, even though we talked about writing numbers or typing in numbers in scientific notation on your calculator, we did that way back in chapter 1. So if you haven't practiced it too much since then, or since chapter 8, or whenever we last did this, I think it was actually chapter I believe it was chapter 7. I think it was where we had Avogadro's number and a lot of really large numbers in scientific notation. So if you haven't practiced it since then, doing these calculations, it's kind of important to get the hang of this, because I find that the students often make a lot of mistakes here on this. Okay, so if you are having trouble remembering it, I recommend pausing this video, going back to chapter 1, and rewatching that section where I talk about using your calculator here. Or just ask me during office hours and I'll help you. Anyway, you do that, and you should get an answer of 5 times 10 to the negative 13 molar. Okay, so that's our concentration of H plus. So let's compare that to our concentration of OH minus, which is 2 times 10 to the negative 2. Which of those numbers is bigger? Now remember, that exponent, okay, that exponent that comes after that times 10, that gives us the scale that we're dealing on. Okay, so both of these are small numbers, but which one's smaller and which one's bigger? So since negative 2 is less negative than negative 13, our hydroxide ion concentration is the bigger number. So if OH minus is greater than H plus, that tells us that we're dealing with a basic solution. Okay. Now, you've seen in that last example, when it comes to dealing with with these numbers, we're dealing with really small numbers. We're dealing with things that we have to write out in scientific notation, and as you probably remember, that's kind of a pain sometimes, especially when you're trying to do calculations with it and you're punching these numbers into your calculator. Okay, using your calculator's exponential form, writing things out using the EE button, usually on a TI-84, makes that a little bit quicker and easier to do, but it's still a lot of numbers you've got to punch into your calculator. Okay, you're still dealing with a really large scale because of just how tiny these numbers are. Okay, well, what we do instead to make the numbers a little bit more manageable is we use what's called a pH scale. Now, to understand the pH scale, I've got to explain what the P stands for in pH and how it works. The P there stands, it comes from a German word, potens, meaning power. Okay, what we do is we actually take the negative log to the base 10 of the number, of any number, to get the P version of that. Okay, so we're not going to do this here, but for example, with Ka values, you can take the negative log of them to get pKa values. So those of you who go on to Chem 111 and 112, or go on to Organic Chemistry 203, 204, you'll find that we actually don't talk about Kas that much, but we talk about pKas a little bit more, just because those numbers are easier to deal with. Okay, so whatever your number n is, to get P of that number, you just take the negative log of that number. Okay. By the way, if you don't see a base written here, it's automatically log base 10. Okay. I'm kind of speaking to a lot of people, to those of you who have seen logs before. that's where different bases matter. For those of you who haven't dealt with logs before in math, don't panic. Everything we're going to do here is log base 10. I'll show you how to do that, and it's really straightforward. We're not going to do anything involving changing of bases or any of the other weird logarithmic stuff that you may have to do in a math class. When it comes to logs in chemistry, things are relatively straightforward here. Okay, so what does this mean? Well, when we punch this into our calculator, we would take a number. Now, it depends on the type of calculator you have. Some of you may have to punch in the value of n and then hit the log button after that. Sometimes you have to punch in this whole thing, like type in, the plus minus sign, log, then the number, and then hit enter or equals, and your calculator will give you the answer. It's one of those two. If you get stuck, just let me know. I'll help you. Okay, but basically, you take that negative log. You take the log base 10 of your number, and then you multiply by -1 or flip the sign, and that'll give you the p version of that number. So what is pH? Well, the H in pH comes from hydrogen. So pH is the negative log of our hydrogen ion concentration. Okay, so here we have written as H+, but remember it could also be hydronium, H3O+, probably the better way to write that. But anyway, that's where that H in pH comes from. Okay, so we just take the negative log to the base 10 of our hydrogen ion concentration. And when we do this, it takes a number in scientific notation and it shrinks it down. It makes it a much more manageable number. All right. Now, you've probably heard somewhere that the pH scale runs from 1 through 14. That's technically not entirely true. Those are where the most common numbers are, but you can technically go beyond that. It's possible to have a pH lower than 1. It's possible to have a pH above 14. It's just not very common. So yeah. So as far as we're concerned, for most intents and purposes, you'll see the pH range being somewhere between 1 and 14. Okay, so that's way more convenient than having to deal with numbers in scientific notation. So let's see a practice problem to see how we do that calculation. So let's say we have an acid that has an H+ concentration of 1 × 10 to the -4 molar. How do you find the pH of this solution? Okay, and again, I recommend following along on this with your calculators to make sure you're getting the hang of doing this calculation. So remember, pH is negative log of our H+ concentration. So we want to take the negative log of this number. So again, depending on your calculator, you may want to type in that number and press the log button, and then flip the sign. You'd multiply it by -1. Okay, or depending on your calculator, you may use your plus/minus button, log, and then type in the number 1 × 10 to the -4. Okay, and close parentheses and hit enter. But either way, you should get a final answer of 4. Okay, if you take just the log of 1 × 10 to the -4, you would get -4 as your answer. So all that negative sign in the front of the formula does is it just flips that sign. It gets rid of it, and that's why your final answer here is positive. Okay. All right, so again, not that a negative pH is impossible. It is possible to have a very strong concentration, a sample that has a very high concentration of a strong acid that can have a negative pH, but again, not very common. All right, so this was a very straightforward answer. In case you're wondering why that number happens to coincide with your pH, it's because your coefficient here is 1. So if you don't have a calculator and your coefficient is 1, you can actually do this without a calculator. Whatever your exponent is, that becomes your pH as with the sign flipped. But that being said, this coefficient isn't always 1, so having a calculator handy to do this, this is why you need a scientific calculator for this class. A simple 4-function calculator won't have a log button. Okay, so if you have even a simple scientific calculator, like I said, back in chapter 1, if it's it shouldn't cost you more than $15, that's how you can calculate this. Okay, let's practice this. Here we have a solution that has an H plus concentration of 1 times 10 to the negative 3. What's its pH? The second question here is a little bit trickier. Instead of giving you the H plus concentration, they give you the OH minus concentration. Okay, so watch out for that. Okay, you want to perhaps first calculate the H plus concentration from this number and then figure out the pH. Okay, so I'm going to pause this video for a second, or you should pause this video for a second, and then see if you can calculate these answers and check your work. Okay, so with that first one, we had the H plus concentration given to us directly. So finding the pH is straightforward. You just take the negative log of that number. And it's easier than that because since your coefficient over there is 1, you know that even without a calculator, you can figure out that your pH is going to be 3. All right, but I recommend that you try this out with your calculator anyway, just to confirm that and get the hang of using logarithms on your calculator, because you're going to need that for your next problem. In the next problem, they give us our OH minus concentration. Now, because for your pH you need the H plus concentration, we can't plug in the number the question gives us. We have to first convert that into our H plus concentration, and to do that, we're going to use kW. Okay, so they've given us the OH minus concentration. We know that kW is 1 times 10 to the negative 14. How do we get H plus? Okay, we did that earlier. We did some problems with that. Remember, these two numbers are being multiplied. So to figure out H plus by itself, you would divide by OH minus. So the question told you had an OH minus concentration of 5 times 10 to the negative 5. So you divide by that number, and that gives you an H plus concentration of 2 times 10 to the negative 10. Okay, now we've got an H plus concentration. Now we can just take our negative log and we'll get the answer. Now, again, we can see from our coefficient that we're not going to get a simple whole number answer. We're going to get a decimal. And so try that out. Okay, take the negative log of that number, and hopefully you should get something in the ballpark of 9.7. All right. So hopefully that's what you got. If not, please, play around this. It might take a little getting used to how your calculator does logs. And if you get stuck, as always, just let me know, and I'll be happy to walk you through it during office hours. Okay, so as I pointed out, the pH scale involves logs base 10, and it really shrinks the scale that you have to deal with when it comes to hydrogen ion concentration. So the reason for this is that as a logarithmic scale, you have a tenfold increase with every single step of pH. So a pH 3 solution is 10 times more acidic than a pH 4 solution. It's not 1 more time, it's 10 more times. Okay, even though the difference is just 1 on the pH scale. All right, so it's something to keep in mind there. All right. In case you're wondering why that is, if you think of the numbers in scientific notation, when you have times 10 to the power of something, you're changing that exponent by 1. But it's because of that times 10, that's why that scale is, is increased tenfold. Okay. So the other thing to watch out for with pHs is that negative sign, right? Because of that negative sign, pHs change a little bit differently. So remember, when you increase the concentration of H plus, that exponent in your H plus concentration in scientific notation is going to get less negative. So what does that mean for a pH? Well, your pH is actually going to get smaller. All right, so this is just a quirk of having that negative sign in the formula. So a lower pH actually means a higher H plus concentration and therefore a more acidic solution. Okay, so how do we measure pH? We've seen how to calculate pH, but if we could measure pH, that'd be a quick and easy way to determine if a solution is acidic or basic, or how acidic or basic a solution is. And conveniently, we have ways to do that. You can either measure your pH using some sort of pH indicator or using a device called a pH meter. A pH meter has a probe that you dip into your solution, and the device will give you a digital readout of what the pH is. Actually, I shouldn't say it'll give you a digital readout. There are pH meters that have analog readouts. But my point here is it will directly tell you what the pH is. The other way to determine the pH is to use an indicator. Now, an indicator is a chemical that changes color based on the pH it's under. Okay, so if you put it into a solution of a particular pH, it will have a particular color. That color will tell you what the pH is. Okay, now here I've written down you could use pH paper. pH paper is just paper that has an indicator absorbed onto it. Okay, so the paper itself changes color. Okay, you're going to see both of these sources of pH measurement in Lab 13, where I basically use red cabbage juice as an example of a pH indicator, and we use a pH meter and we look at a bunch of different household chemicals and see what their pHs are. All right. We'll also look at buffered solutions, which is something you'll see later on in this chapter in that lab. So, if you haven't already done so, do check that lab out. Okay, so we've talked a lot about pH so far. I'm going to introduce something similar, and that's pOH. Now, pOH is, as the name suggests, is kind of like pH. The only difference is we have OH instead of H. Now, remember, OH here comes from hydroxide ions, OH minus. So instead of using our H plus concentration, okay, from our protons or hydronium, we're going to use hydroxide. Okay, and remember, those two things are related. Our H plus and our OH minus are tied together with Kw. So we can calculate one from the other. Okay, and I'll show you a shortcut or a little simpler way to tie all of these together in a little bit. But we'll come to that in a little bit. Let's look at an example of calculating a pOH from an OH minus concentration. So let's say we have a solution that has an OH minus concentration of 1 times 10 to the negative 4 molar. How do we find the pOH? Well, you just take the negative log of that, right? And this problem will probably look very, very familiar because we calculated a pH under similar circumstances. But basically, you take the negative log of that number, which winds up being 4. We have a pOH of 4. Okay, but the key thing to realize here is that we calculated our pOH from our OH minus concentration. Okay, so if you take the negative, in order to find our pOH, we've got to take the negative log of OH minus. Okay, so please note that what's here in your square brackets lines up with what's after the P here. I point this out because a lot of students make a silly mistake where if you're given H plus, you take the negative log of that, you would get the pH, not the pOH. Likewise, if you're given OH minus and you take the negative log of that, you get pOH and not pH. And sometimes to trick you, a question will give you one and ask for the other. And so you've got to do that conversion in the middle. Again, I'm going to show you a shortcut for this in a second. And here's that shortcut. Basically, if we take our Kw expression, where H plus times OH minus concentration gives us 1 times 10 to the negative 14, and we just take the negative log of that whole equation, it actually gets simplified to pH plus pOH is equal to 14. All right. That plus sign is just an artifact of how logs work. Okay, so it's a plus sign, not a multiplication sign. But this is the really convenient thing for relating our H plus and OH minus concentrations. If you have them present in pH or pOH, you can easily find one of those given the other. Just subtract it from 14. So to summarize this, basically our 4 terms that we have here are H plus, OH minus concentration, pH, or pOH. And we can relate the 4 of them through multiple ways. We can get from one corner of this to another corner through multiple pathways, but you'll probably find one is easier than the other. If you're like me and you don't like typing numbers in scientific notation, into your calculator, you probably really dislike this step over here. Okay, so if you want to avoid that, you can get into pH or pOH and relate the two by knowing that they add up to 14. Okay, so for example, earlier in this, just a few slides back, I had a problem where I gave you an OH minus concentration, and I asked you for the pH of that solution. Now, there's no way to do that directly, so what we did was we took our OH minus concentration, we took 1 times 10 to the negative 14 and divided by that number, and we got the H plus concentration. And then we took the negative log of that, and we got the pH. All right. So that's how we did that problem. But again, it involved us using numbers in scientific notation. Now, instead of going that way, what I could have done instead is taken the negative log of OH minus, and that would have given me my pOH. And then I would have subtracted that from 14 to get the answer. And you get the same answer. It's not like you have a risk of getting the answer wrong that way. It's the same answer. It's just the math is probably a little bit easier to do to set up. Okay, but that being said, again, like if you are comfortable with numbers in scientific notation and you prefer doing the calculation this way, both of those will give you the same answer, whichever way you go. Whether you go from here to here to here, or from here to here to here. Okay, a quick note here about getting out of pH. You'll notice that to do that, we take 10 and raise it to the power of negative pH. That'll give us our H plus concentration. It's the reverse of a log base 10. Okay, and the same thing for our pOH to OH minus. You take 10 raised to the power of negative pOH, and that'll give you the concentration of OH minus. All right. If you want to see how that's done, I guess I could show you that really quickly here. If we know that pH is equal to negative log base 10 of our H plus concentration, and we want just the H plus concentration, right? We're trying to get that from pH. Well, first let's get rid of that negative sign. Okay, so I'm going to move negative here and get rid of that. Basically, if I multiply both sides by -1, that's what will happen. Now, how do I get rid of that log base 10? Well, the opposite of a log base 10 is 10 to the power of. Okay, so if I take both of these terms and put them as exponents to a base of 10, so 10 to the power of negative pH and 10 to the power of log base 10, well, that cancels that out. And so I have just H plus is equal to 10 to the power of negative pH. And that's what I've done here. And of course, a similar setup for OH minus. Okay, so once you have pH and pOH values, the key thing is, again, if I pointed out earlier that your pH value will decrease as you get more and more acidic. The pOH scale is just opposite, right? So your pOH will increase as you get more and more acidic. And you'll see the opposite here for things that are basic. As something gets more and more basic, your pH increases, but your pOH decreases. And notice that all of, whatever combination you have of pH and pOH, it will add up to 14. Okay? Now, notice that in between here, when your pH, when your hydronium and hydroxide concentrations are equal, right, you have a neutral solution. I think we've seen that before earlier in this PowerPoint. Well, that means that your pH is at 7. So that's something to keep in mind. A pH of 7 means that your pOH is also 7, and that means that you've got a neutral solution. So typically, since we typically look at pH, any pH that's lower than 7 means that you have an acidic solution. Any pH that's above 7 means that you have a basic solution. Okay, so keep that in mind when you're looking at your actual pH values. Okay, let's try some examples of of these calculations. And again, if when you're doing this, feel free to go back a few slides to where we have this table over here to kind of summarize how we convert one thing to another. Now, please note that a formula sheet will typically tell you that your pH is equal to negative log H plus, and it will give you the Kw expression that H plus times OH minus gives you 1 times 10 to the negative 14. You would have to derive the rest of the stuff yourself, okay? But if you want to get the hang of it, this table over here, or this diagram over here, kind of summarizes how to interconvert these 4 types of variable. Okay, so let's try that out. A sample of rain in an area with severe air pollution has a pH of 3.5. What is the pOH of this rainwater? Well, now this question relates pH and pOH, so this is probably going to be a relatively easy question. Think back to the formulas we've looked at, and how are pH and pOH related together? Well, if you recall, pH plus pOH adds up to 14. So if we wanted to find pOH, we just have to subtract pH from 14, which was 3.5, so pOH must be 10.5. Okay, that was pretty straightforward. Okay, so these calculations don't have to be hard necessarily. All right, let's try one that's slightly harder. The pH of rainwater in a polluted area is found to be 3.5. Okay, again, similar numbers, that's just a coincidence. What is the H plus for this rainwater? Okay, so we've seen that pH is equal to negative log of H plus, and that gives us 3.5. And of course, this formula would probably be given to you, but you're not being asked for the pH. You're already given the pH. You want to do this backwards. You're trying to find that H plus concentration. Okay, so you have to be able to derive that yourself, or just memorize that. Basically, to do this backwards, your H plus concentration is 10 to the power of negative pH. In this case, since your pH is 3.5, it's 10 to the power of negative 3.5. Now, you can't leave your answer like this. This is not an answer because your exponent is a decimal. It's not a whole number. That's not how scientific notation works, right? Scientific notation always has a whole number exponent. Okay? So you actually have to plug this into your calculator. Now, to do this, you would type in the number 10. To put a exponent, depending on your calculator, you might use the caret button. The caret button is the one that looks like this. Okay, so you would type in 10 caret, then use a plus minus button, and 3.5, and then hit enter or equals, and that'll give you the answer. Some calculators don't have a caret button. They might have something that looks like an XY button like this. So you would hit like 10 and then XY and then the rest of this to represent what the Y is, and that would also do it. But anyway, whichever way you do that, you should get somewhere in the ballpark of 3.16 times 10 to the negative 4 molar. Okay, so yeah, again, I really recommend practicing this. Like, try this out right now with your calculator to see that you're able to do these calculations on your calculator easily. Okay, so you definitely want to get the practice out of the way here and during your homework rather than trying to figure it out for the first time on a test. Okay, why don't you try this one out? Okay, so here we have pOH of a liquid drain cleaner is found to be 10.5. What is the OH minus concentration for this cleaner? Okay, so ask yourself, how are pOH and OH minus related to each other? Okay, it's going to be very similar to the previous problem, so hopefully you guys figured that out. You take the 10 to the power of, I've written this here as an inverse log, but it's really just 10 to the power of that negative pOH. And you should get that, that concentration accordingly. You should get 3.16 times 10 to the negative 11 molar. Okay, so how do we calculate pH for solutions? We've seen how we can measure them using a pH meter or an indicator, but sometimes it helps to be able to do the calculations. Now, in the case of strong acids, this is actually really easy, and the reason for this is that these are strong electrolytes, right? We know that our acid is completely going to dissociate into H plus and the conjugate base. Well, if that's the case, our concentration of H plus, stoichiometrically, should be the same as the concentration of the acid we started with. Well, if we know that, then we can just find the pH by taking the negative log of that number. So let's see an example here. What's the pH of a solution of 5 times 10 to the negative 3 molar HCl? Okay, so we have a 0.005 molar solution of HCl. How do we calculate the pH? Well, for the pH, we need the H plus concentration. So what's the H plus concentration of 5 times 10 to the negative 3 molar HCl? Conveniently, since hydrochloric acid is a strong acid, we know that it's going to be the same number, because HCl, being a strong electrolyte, splits up into H plus and Cl minus. Well, for every 1 HCl, we have 1 H plus. So if you have 5 times 10 to the negative 3 of these, you're going to have 5 times 10 to the negative 3 of these. And so, because of that 1-to-1 ratio, it's just the same number for your H plus concentration, and therefore to find the pH, you just take the negative log of that number. And so you can try that out, and you should get 2.3. Okay, but that's basically it in a nutshell. That's how you do that for a strong acid. For weak acids, this gets a little bit more complicated because you have a partial dissociation. So your concentration of H plus is not going to be the same as your initial concentration of acid. So to do that, you actually need the Ka value of your acid, and then you pretty much set it up like an equilibrium problem like we did in the last chapter. Okay, where you'd solve for the H plus concentration. We're not going to do that too much over here. We're going to do similar problems later on when we look at buffered solutions. But if you do go on to Chem 111 and 112, that's how you would do a problem like that. You would treat it just like an equilibrium problem like we saw back in chapter 11. Okay, so let's talk a little bit about these acid-base reactions. We've kind of talked about them already when we looked at the Bronsted-Lowry definition of an acid and a base. They kind of need each other, right? You need an acid and a base to react with each other for them to be acids and bases. We call the reaction of an acid and a base a neutralization. Specifically, it's where an acid and a base react to form a salt and water. Okay, now what is a salt? A salt, by definition, is just an ionic compound that is the product of an acid-base reaction. All right, it's the conjugates of our acid and our base that form our salt. Those ions are the same ions that make that salt ionic compound. The H plus from our acid and the OH minus from our base are what go on to form the water. Okay, so let's have a look at an example here. So let's say we have the reaction between hydrochloric acid and sodium hydroxide. Now, please note, this is a double replacement reaction. Okay, I kind of talked about this way back in chapter 6 when we talked, or sorry, chapter 7 when we talked about types of reactions, and I gave you examples of double replacement reactions and explained what drove them forward. We've seen precipitation reactions where the formation of that precipitate causes that reaction to be driven forward. In the case of the acid-base reaction, it's the formation of water that drives us forward. So let's have a look here. So here we have HCl, hydrochloric acid, reacting with NaOH, sodium hydroxide, and we know we're going to get a salt and water. Now, what's our salt here? Our salt here is just table salt, sodium chloride. We have the sodium ions, right, which are the conjugate acid of our base, and the chloride ions, which are the conjugate base of our acid, and we combine them to form our salt. Okay, so we have an acid reacting with a base to make a salt and water. Okay, so again, please note that sodium chloride is just a type of salt, even though it's commonly known as salt. Its real common name is table salt. And so when I say that you get a salt and water, your salt's not always going to be sodium chloride. It kind of depends what your acid and base are. So if we want to see this acting as a double replacement reaction, it might help to see this as an ionic and a net ionic equation. So if we were to take turn this into an ionic equation, anything that is aqueous gets split up into its ions. Now, very conveniently, all of these ions have a plus or minus 1 charge. So HCl splits up into H plus and Cl minus. Sodium hydroxide splits up into Na plus and OH minus. It's a polyatomic ion, hydroxide. Sodium chloride, which is also aqueous, splits up into Na plus and Cl minus. Water, which is a liquid, stays water, right? It doesn't ionize here. So, what are our spectator ions in our ionic equation? Well, you've probably noticed that sodium and chloride are canceled out on both sides of that arrow, right? We have Na plus on the reactant side, Na plus on the product side of that arrow, and same with chloride and chloride. So what's the net ionic equation here? H plus from our acid reacts with the OH minus from our base to give us water. And the nice thing here is that this is true for every acid-base equation. Every acid-base reaction has our H plus from our acid and our OH minus from our base forming water to make our net ionic equation. Now, again, this is why we call our sodium ions and chloride ions here spectator ions. We could swap those out for any other conjugate acid or conjugate base, and our net ionic equation will be the same. Okay, and this is why this works for every acid or base, every acid-base reaction, every neutralization reaction. Okay, you can play around with what these spectator ions are. So, the nice thing here, actually, is to also notice that H plus and OH minus always react in a 1-to-1 ratio to make one water molecule. There's one H plus reacting with one OH minus to make one water. Well, the nice thing here is this makes it easy to balance these equations because you know that they have to react in that 1-to-1 ratio there. So even if your acid or your base has more than one H plus or more than one hydroxide, you can then figure out how many you need of the other chemical to balance it out. So let's look at an example here. Let's say we want to balance out the neutralization reaction of HCl with barium hydroxide. Okay, so let's write these out just generically. So we know HCl is our acid, BaOH2 is our base, and we know we're going to get a salt in water. Now, again, this is not balanced yet. Don't worry, we're going to get to that. We're going to see how to balance this in a second. But I want you to start off with the sort of skeleton of a reaction. We know that our acid plus our base will give us salt and water. Now, we don't know what our salt is yet, and we haven't balanced this, but we'll get there. So, now we know that our base has two hydroxides, so we know we're going to need two hydrogens. So we're going to balance out our two H pluses by having two HCl's. Since every HCl has only one hydrogen ion, and we know that we have to have the same number of hydrogen ions as hydroxide ions, which is 2, and that tells us we need to put that 2 over there. You're probably going to figure out what I'm going to say next, right? Remember, our net ionic equation has one hydrogen ion and one hydroxide ion making one water molecule. Here we have two hydrogen ions and two hydroxide ions. How many water molecules do you think we're going to have? You've probably guessed, to balance this out, we're going to need 2 waters. Okay, so here's everything balanced out. So now the only thing we're missing is the formula of the salt that we make. Well, remember, we know that the cation is going to come from our base, and our anion is going to come from our acid. So we know that we have Ba and Cl. But now the numbers of those ions have to agree with everything else you've balanced. So you know that there's going to be only one barium because there's only one barium in our one barium hydroxide. And you know that there's going to be 2 chlorides because even though there's only one chloride in HCl, there are 2 HCl's, which means we have 2 Cl ions. So the formula of barium chloride is going to be BaCl2, and this equation is balanced. Okay. Now, you're probably saying to yourself, okay, that was really dumb. we know that the formula of barium chloride is BaCl2. We learned that back in chapter 5, right? Barium's in group 2, it has a 2 plus charge. Chloride is in group 17, so it has a -1 charge. Of course, you're going to need 2 of those negatively charged chlorides to balance out the 2 plus charge on your barium ion. That's great. But my point here is that this is a great way to check your work. Okay, so you can either balance it the way we've done here and then use what we learned in chapter 5 to check that you did it correctly, or vice versa. You could have started off with that formula BaCl2 and then balance the equation and then done it this way to make sure you did it correctly. Now, I pointed out that H plus and OH minus react in a 1-to-1 ratio. This is very useful from a stoichiometry standpoint. And more importantly, we have an analytical technique called titration that takes advantage of this and allows us to calculate something that's missing using information of a known chemical, something that we have all the information on. Okay, so the last lab that we actually do in this course is a titration lab, so do check out that video too if you haven't already. So you'll see in that video that we'll do a titration of vinegar with sodium hydroxide. So we actually have a very similar setup here in this diagram. So in the lab that we do for lab 14, you take a sample of vinegar. You take you could take in the lab we take 5 milliliters. Here it looks like they're measuring 20 milliliters. But my point here is that you have a set volume, a very accurately, precisely measured volume, and you put that into a container. We usually use an Erlenmeyer flask. Those are easier to use for this experiment. Now, you know the volume here. You've measured it very carefully. We don't know the concentration of this acid. In this device here called a burette, it's a long glass tube with volume markings on it. We're going to put in a base, all right, of a concentration that we know. So if we're using vinegar here, acetic acid, we're going to put our base here, and we have to make sure it's a base that we know the concentration of. So here we're using sodium hydroxide, and it's a sodium hydroxide solution that we have the concentration for. Okay, either we make it ourselves or someone gives it to us and tells us what the concentration is. Now, you have to have an indicator present in this solution, but when you add your base to it, all right, you're neutralizing the acid that's present here. Now, your indicator will change colors once all of this acid has been neutralized, and that's what happens here. Okay, so once your solution has changed color, you know that you have added enough base to neutralize the solution. Okay, so you want to do this very carefully so that you add just enough base. You don't add an excess. Now, if you make a note of your initial volume and your final volume, well, now you have 2 pieces of information about that sodium hydroxide. You know the volume that was used, and you know the concentration that was used. As we saw in a couple of chapters ago, if we have a concentration and a volume, we can figure out the number of moles of our solute. And as I pointed out, that gives us, while we have the concentration of hydroxide, that's going to be the same as our concentration of H plus in our acid. And so now if we have our concentration of acid and we know the volume that we measured very, very carefully earlier in the experiment, now we can calculate the concentration of that unknown acid. Okay, and that's essentially what we actually do in lab 14. You figure out the concentration of acetic acid in vinegar. So what does this titration look like? How does your indicator change? Again, you're going to see this in the video for lab 14, but here's actually a picture of what it looks like. The indicator we use in that lab is called phenolphthalein. It is, it's colorless in acidic solutions, but it turns pink in basic solutions. So as soon as you neutralize your acid completely, it turns this pink color and stays. Okay, so where the drops of sodium hydroxide hit your vinegar, it turns pink temporarily, but since there's an excess of vinegar in here, that pink color disappears. As soon as that pink color stays, you know that you've reached the end point of your titration. And at that point, you would make a note of your final volume of sodium hydroxide. Okay, so that's how we do the calculation. We, using the concentration and volume of our base, we can figure out our moles of acid accordingly, and using the volume of the acid, we can figure out the concentration. Please note that in this experiment here, we've used the acid in the Erlenmeyer flask and the base in the burette. It doesn't have to be that way. You could have them the other way around. Basically, the burette contains the solution that you know the concentration of. Your Erlenmeyer flask here contains the concentration of the chemical you want to find out. Okay, so let's talk a little bit about those salts that are formed from our neutralization reactions. Okay, so are these salts going to be acidic, basic, or neutral? Now, before this class, you probably thought that's kind of a silly question, right? Salts are salts. They're not acidic or basic, right? They have to be neutral. That's not actually the case. It turns out that the ions in your salts may themselves have an effect on water. So let's look at 3 scenarios here. Okay, let's look at salts that are formed from a combination of strong or weak acids or bases. So let's say we use a strong acid and a strong base to do our neutralization reaction. What is the salt we're going to make? The salt winds up being neutral. We get a neutral solution. If you have a solution of this salt, it would have a pH of 7. Okay? So, why is this? Well, the reason for this is that your salt is made from the conjugates of strong acid and strong base, which means that they themselves are really kind of worthless conjugates. They don't do that reverse reaction. Let me give you an example here. Let's say we have potassium nitrate. All right, so potassium has a cation K+, which comes from the strong base potassium hydroxide, and nitrate, its anion, comes from the strong acid nitric acid, HNO3. Okay, now think about those reactions. How does potassium hydroxide act as a base? Well, it's a strong base, which means it's a strong electrolyte, meaning it completely splits up into K+ and OH-. Okay? But remember, it's a strong base. That reverse reaction will not happen. K+ does not want to go back to forming KOH, which means that K+ will not react with water to form KOH, which means that K+ is kind of worthless as a conjugate base. It doesn't act as a base. Likewise, nitrate comes from the strong acid nitric acid. It does not want to do that reverse reaction to go back to being nitric acid, because it comes from nitric acid, which is a strong acid. Nitric acid really wants to form nitrate and hydronium and not go back to being nitric acid. Okay, so nitrate is also worthless as a conjugate base. And as a result, both of these ions don't influence pH. Okay, and so the salt made from those ions is going to form a neutral solution. Okay, that's great. What about the other 2 combinations? What if you have a strong acid reacting, a weak acid reacting with a strong base? Well, that's going to form a basic solution. And the reason for this is that the conjugate base of a weak acid is actually a decent base. That weak acid is going to be in equilibrium with its conjugate base, and therefore that reverse reaction allows that conjugate to react with water and give off hydroxide ions. Let's look at an example here. So here we have potassium bicarbonate. Okay, what's our cation and what's our anion here? Well, K+ is the cation potassium, and as we saw previously, it comes from the strong base potassium hydroxide, so we've already seen it's kind of worthless. But what about HCO3 minus? That's the anion, or the conjugate base, from carbonic acid, H2CO3. Okay, if you're having trouble seeing this, you take HCO3 minus and you just add an H plus to it, and you'd get the formula of its acid. And carbonic acid is a weak acid, which means that if this is an equilibrium, which means that you're going to have a balance between these. So some of your carbonate is going to form carbonic acid. Okay, whereas potassium does not do this with water. Okay, it's not going to react with water. It doesn't want to form potassium hydroxide. But bicarbonate does want to form carbonic acid, and when it does so, it gives off hydroxide ions. Okay, so that conjugate base of carbonic acid is a decent conjugate base. And of course, we've got this other situation where a strong acid and a weak base might react, and it turns out that that forms an acidic solution. It's because the conjugate acid of your weak base is a decent acid. Now, the only weak base you guys have seen so far is ammonia, and so its conjugate is ammonium. So any ammonium salt, NH4 as you can see here, like ammonium chloride, will do this. The chloride is the anion of hydrochloric acid, which is a strong acid. So again, chloride's not going to do anything to the pH. It's kind of worthless as a conjugate base. But ammonium is going to do this. It's going to react with water and go back to forming ammonia. Okay? But when it does so, it gives off hydronium ions, and this is what makes the solution acidic. Okay, so it turns out that ammonium is actually a decent conjugate acid for ammonia, which is a weak base. Okay, so now you've probably noticed that there's a fourth situation where you could have a weak acid and a weak base react. That's a little bit beyond scope of this class. In order to calculate what's going to happen, you need to know the Ka and actually the Kb of your weak acid and your weak base. And it involves an interesting equilibrium problem, and even that would be a little bit tougher than something you'd see in Chem 103. But if you go on to Chem 111 and 112, that actually would be a type of calculation you'd be able to do. You'd be able to look at a salt that's formed from a weak acid and a weak base and determine whether it's going to be acidic or basic. Okay, but anyway, we're not going to look at that situation. So there's only three scenarios here, right? We have a strong acid and a strong base, and that'll give us a neutral solution, a neutral salt. A strong base and a weak acid will give us a basic salt. Okay, and a weak base and a strong acid will give us an acidic salt. So again, how can you figure out what you're dealing with? Since you don't see the acid and the base, you're just seeing the salt in front of you. You kind of have to have a little bit of imagination when you look at the ions that your salt is made from. Okay, so think about what forms strong bases. Okay, a strong base has a group 1 or group 2 metal ion, right? Because those hydroxides are strong bases. Look at your strong acids. Remember, it's hydrochloric acid, nitric acid, sulfuric acid, perchloric acid. Those anions come from those acids. So if your salt contains them, that means the acid must have been a strong acid. Okay. For a weak base, pretty much the only one you've got to worry about is ammonium, right? You're not going to see too many other examples. And so again, like based on the ions you're seeing, you can kind of figure it out. So since you've memorized your strong base ions, the group 1 or group 2 metals, and you've memorized your strong acid ions, it should be pretty easy to recognize those. And like I said, with your weak base as well. So even though you don't really need to memorize your weak acids, there's lots of examples of weak acids. I really don't expect you to memorize all of them. You can kind of figure it out if you don't see one of those strong acid anions. So yeah, so essentially, like, if you look at your ionic compound and look at the ions it splits up into, ask yourself, where did those ions come from? What base gave me my cation? Okay, if you see, like, metals like sodium, magnesium, potassium, you know it came from a strong base. But as soon as you see ammonium, you know it came from a weak base. Likewise for your anions, if you see like things like chloride or nitrate, you know they came from strong acids. But if you see anything other than those things, like like carbonate or bicarbonate or nitrite or things like that, you know they came from a weak acid, even if you haven't memorized those weak acids. So let's practice this. Here are three salts, three ionic compounds. Ask yourself, which of these is going to be acidic, basic, or neutral? Okay, and each of these is one example of of those types. So you're going to have one acidic salt, one basic salt, one neutral salt in these three examples. Okay, so feel free to pause this here. But again, you want to split these up into their ions and ask yourself, where did these ions come from? Okay, so hopefully you figured out that, so even if you didn't do this in order, the easiest one to figure out is this ammonium bromide down here. As soon as you see ammonium, as soon as you see NH4 plus, you know it's going to be an acidic salt. You know ammonium comes from ammonia, which is a weak base. So ammonium must be the conjugate acid of that weak base, and therefore this is an acidic salt. Okay, so that one hopefully was really easy. For the other two, so lithium is a group 1 metal. Okay, so we know that came from a strong base. S, that's not sulfate, nitrate, or chloride, or perchlorate. So you know that this is probably from a weak acid. Okay, so remember, strong base and weak acid gives us a basic salt. Okay, and then here we have magnesium nitrate. Magnesium comes from magnesium hydroxide. Right, it's a group 2 metal, magnesium there, and so magnesium hydroxide is a strong base. Nitrate comes from nitric acid, which is a strong acid. So you know that this is going to be a neutral salt. And that brings us to buffers. Buffered solutions are ones that keep pH relatively constant, even when acids or bases are added to your solution. So in the case of an unbuffered solution, when you add an acid, the extra hydronium ions cause your pH to drop. Likewise, when you add a base, the extra hydroxide ions causes your pH to rise. Okay, so you can see here in this example, we have some distilled water, and of course it starts off with a pH of 7. You can see that adding an acid causes the pH to drop down here and rise over here in the case of adding a base. However, if we take a buffered solution and we do the same thing, the pH will still change. Our pH still drops slightly when we add our acid and still rises slightly when we add our base. But the fact is that it doesn't change that much. You can see that the change is far less drastic than in the case of the unbuffered solution. Okay, so what are buffers and how do they work? So the key thing here is that buffers absorb extra hydronium and hydroxide that come from our acids and bases. Okay, and now these are pretty important. There are a lot of applications where you need your pH to stay relatively constant. In industry, you want to keep the pH relatively constant to make certain reactions run optimally to increase the amount of product you make in a factory, for example. In the body, you need your pH of your blood, for example, or cell cytoplasm to stay relatively standard, because otherwise certain enzymes might not work properly. So basically, again, like the whole idea is you want to keep the pH at a particular level, and it's very important for these solutions to have that constant pH. So buffers are needed to absorb any extra acid or base that's added. So how do buffers work? Well, the key thing that you need for a buffer to work is an acid-base conjugate acid-base pair of a weak acid or base. Okay, so what does this mean? Well, it means you need either a weak acid and its salt, okay, or a weak base and its salt. All right, so we'll look at some examples in a little bit, but at the heart of a buffered solution is that equilibrium between an acid or a base and its conjugate. And so in order to have that equilibrium, it's very important that you choose a weak acid or a weak base. So let's see some examples. So here we've got some examples of acids and their corresponding salts, or hopefully corresponding salts, right? The way to tell that you've got a salt is essentially you have one of the hydrogens of your acid replaced with a metal ion of some sort. Okay, if we were using a weak base like ammonia, we would basically use an ammonium salt of some sort as our salt for that buffered solution. But it looks like all the examples here involve acids. Okay, so let's go through each of them. So in this first one, we have HCl, and the salt that we use is KCl. So we can see that we've replaced the hydrogen with a potassium ion. Now, is this a good combination for a buffered solution? We do indeed have an acid and its salt here, but remember, one of the requirements is that you use a weak acid, and hydrochloric acid is not a weak acid. Okay, so that is not a buffered solution. Now look at the second example here. We have carbonic acid, which is a weak acid. Is sodium bicarbonate here a good example of its salt? And the answer is yes, right? We've taken one of the hydrogens, okay, so we've taken that conjugate base HCO3 minus, and we've paired it up with a sodium ion. Okay, so this is the sodium salt of carbonic acid. Okay, so this is actually a good example of a buffered solution. All right, the carbonic acid and the bicarbonate ion from this sodium salt will be in equilibrium with each other. Okay, notice that we're choosing group 1 metal salts like potassium and sodium. The reason for this is you want to make sure that your salt is going to be water soluble. It's very important you pick a strong electrolyte for your salt so that you're going to get a large concentration of that anion, which, remember, is the conjugate of your weak acid. Okay, so B is definitely a good example of a pairing we could use for a buffered solution. Have a look at these last two and decide if they will be buffered solutions or not. Okay, I'll go through the answers in a second, but feel free to pause this video. Okay, so the third one is not a good example, quite simply just because they aren't a pair. They aren't a conjugate acid-base pair. Here we have phosphoric acid. The conjugate base of this would be dihydrogen phosphate. Right? If we remove one hydrogen ion from this, we'd get H2PO4 minus, which we could add a sodium ion to that to turn to a salt. The only problem here is they've used sodium chloride and not sodium dihydrogen phosphate. Okay, so in order for this to be a buffered solution, they should have used NaH2PO4, which they didn't. And the last one is a good example. So here we have acetic acid, which is a weak acid. And we can replace the acidic hydrogen, okay, which is this last hydrogen here, by the way. Remember, this is a carboxylic acid or an organic acid, and it's this hydrogen in our COOH group, that carboxylate group. That's the acidic one. So that's what's missing here, right? We still have that CH3COOH with a negative charge, and we can see that's balanced with a K plus ion. Okay, so this is a good example of a salt of a weak acid. All right, so how does this combination of a weak acid or base with its conjugate work? As I pointed out, it hinges on that equilibrium between your acid and its conjugate. Okay, so when you look at your acid, it will dissociate to form its conjugate base and hydronium, right, when it reacts with water. But remember, because this is a weak acid, I've drawn this here with an arrow, but really this is a reversible reaction, so this should actually have an equilibrium arrow. Okay, so the key thing, though, is because we have a solution of the salt, we have a large concentration of this anion as well as this weak acid. If we had only the weak acid, we'd have a large concentration of the acid and very small concentrations of the products, because remember, weak acids are weak electrolytes. So by adding that a sample of the salt of this weak acid, we increase the concentration of this product over here as well. Okay, so essentially here's that equilibrium we're showing here, and so here's what happens with that salt, right? The salt itself is a strong electrolyte, so it completely dissociates into sodium ions, which are spectator ions that don't really matter, and we have this acetate anion here, and so that's what gives us this equilibrium between the acid and its conjugate. Okay, and we have large amounts of both these things. Now you'll see that having large amounts of both chemicals in both sides of this equilibrium are going to be pretty important because that's what increases the buffering capacity, so to speak, of our buffer. Okay, so what do you want to take away from this here is you've got to remember your weak acid is an acid. It will react with bases. Your conjugate is a conjugate base. And as the conjugate base of a weak acid, it's a decent base. It will react with acids and do the reverse reaction here. So we have a balance between our acid and our conjugate base. And this equilibrium in Le Chatelier's principle will keep the concentration of H3O plus relatively steady. In other words, it'll keep the pH relatively steady. So, how does that work? Well, you start off with large amounts of your acid and base, right? And the conjugate. What happens if we added a strong base to this? Well, our acetic acid, of course, being an acid, will react with the base, the hydroxide ions from the base that you added, and form some more acetate ion using this reaction. So what happens then, of course, is that you have a slight imbalance of your acetate and acetic acid, but the bottom line is that because these two are in equilibrium, they will reach and, well, reach a balance that'll keep the concentration of ions relatively steady and therefore keep the pH relatively steady. What happens if you add an acid? Well, in this case, your acid will react with your acetate anion. So this is the conjugate base of your weak acid. So again, remember, it's a decent base, and so it'll react with that extra acid that you're adding and form more of your acetic acid. So you can see here in our balance, we have more acetic acid than we do acetate, but we still have large amounts of both, and they're still in equilibrium with each other. And therefore, your concentration of ions will stay relatively steady due to Le Chatelier's principle. And again, the bottom line is that because you're keeping the concentration of hydronium and hydroxide relatively the same, relatively unchanged, even though you've added extra hydronium, that extra hydronium is absorbed by this equilibrium, and we keep the pH relatively steady. And so basically that's what buffer action comes down to. You're starting off with large amounts of your weak acid and its conjugate, or you could of course have a weak base and its conjugate, but the bottom line is you have an equilibrium here, and you have large amounts of the two main chemicals in your equilibrium, and adding extra acid or adding extra base will just disrupt this equilibrium slightly. Since you're starting with such large amounts of everything, it's only really a small percentage change that we're making. But the bottom line is those chemicals stay in equilibrium, and it keeps the pH relatively steady. So, how do we determine the pH of a buffered solution? Okay, this is actually kind of a good insight into how to calculate the pH of a weak acid as well. Again, I'm not going to go into too much detail on that. If you go on a Chem 111, 112, you'll get to do a lot more practice with that. But it comes down to recognizing that you have that equilibrium, and therefore you can set up an equilibrium expression. Okay, we can then plug in the numbers from from our equilibrium into there. And solve for our concentration of hydronium. If we have our concentration of hydronium, which is the same as our concentration of H+, well, we can just take the negative log of that to calculate the pH. All right, so you take your equilibrium, the equation for it, right, which is always your weak acid plus water giving you hydronium and the conjugate. Okay, you set up your equilibrium expression, so your hydronium and conjugate are on the numerator as products. On the denominator is your weak acid concentration. Remember, water does not show up because it's a liquid. And that's equal to your Ka for your acid. Well, you can rearrange this to solve for hydronium. So if we multiply weak acid to the same side as Ka and divide by conjugate base, we get this expression, this rearranged expression. Well, if we have these numbers, we can plug those in and solve for H+, or hydronium in this case, and then take the negative log of that answer to get the pH. So let's try some examples. Okay. And again, though, please keep in mind that we So for all the examples we've seen have involved weak acids, so that's why we've been paying attention to Ka. But as I pointed out earlier, you can do this with a weak base as well. So if you have ammonia and some ammonium salt as your buffered solution, you can use the Kb for ammonia. It's a similar setup to a Ka expression. It's just the B stands for base. Okay, and of course you just rearrange it to solve for hydronium, and substitute all the numbers in, and then solve for that, and use that number, take the negative log of that answer to calculate pH. So let's try this out. Here we have a buffered solution where our acid is dihydrogen phosphate and its corresponding base is monohydrogen phosphate. Okay, so you can see it's missing an extra hydrogen. So that's the conjugate base we have present in the buffer. Okay, so here's a conjugate acid-base pair. Now, we're told that our acid here has a Ka value of 6.2 times 10 to the negative 8. We're told that the concentration of both our acid and its conjugate is 0.2 molar. And the question is, what is the pH of the buffer? So let's start writing out the equation for what's going on. Our acid is H2PO4 minus. It reacts with water to make HPO4 2 minus. So notice that we're missing an H plus here. And hydronium, of course. Remember, that's always that product that you get when an acid reacts with water. So when we write out our equilibrium expression, hydronium and monohydrogen phosphate go in the numerator. Our dihydrogen phosphate, which is our acid, goes on the denominator. And that's equal to Ka. So if we rearrange this, we multiply dihydrogen phosphate with Ka, and we divide by monohydrogen phosphate. Okay, and this is our rearranged expression. Okay, it's probably not going to be super important because the numbers happen to be the same thing. You've got 0.2 divided by 0.2, which actually winds up canceling each other out. So in other words, our hydronium ion concentration is just 6.2 times 10 to the negative 8, or the value of your Ka. So how do we find the pH? You're just going to take the negative log of that number. And so you find out that your pH of your solution is 7.21. All right, and that's how you figure out the pH of a buffered solution. So let's try a similar problem out. Okay, so go ahead and try this yourselves. Feel free to pause this video. But to set this up, I recommend writing out an equilibrium equation for carbonic acid reacting with water to make bicarbonate, and then writing out the Ka expression for carbonic acid. Okay, rearrange it to solve for hydronium, and then note that the concentrations and the Ka value that the question gives you, and plug those in. Okay, so just so you know, if you've joined us now having tried this out yourself, here's the equation. Carbonic acid reacts with water to make bicarbonate and hydronium. So when we write out our expression, Ka is equal to hydronium times bicarbonate divided by carbonic acid. Okay, we can rearrange this. So if we multiply by our acid, divide by our base, our hydronium ion concentration is equal to Ka times carbonic acid divided by bicarbonate. Now you can get these three numbers from the question. Okay, so the question tells you that the carbonic acid concentration is 0.2, the bicarbonate concentration is 0.1 molar, and our Ka value is 4.3 times 10 to the negative 7. So when we plug this in, we get 8.6 times 10 to the negative 7 molar for our hydrogen ion concentration. So if we take the negative log of that number, we get a pH of 6.08. And that's the answer. Okay, so that's it for this chapter. And this is our last chapter for Chem 103. So do try out the homework to get ready for the quiz that we have on this chapter. And as always, let me know if you have questions. The next major thing we have besides this quiz and finishing up your labs, if you haven't already done so at this point, is to prepare for your final. So if you haven't already done so, please check out the study guide that I've posted on Blackboard. It kind of breaks down by chapter, what kind of topics you should brush up on to get ready for the final. Kind of broken down by chapter just how much of an emphasis does the exam place on individual chapters. So again, it gives you a feel for, especially if you're strapped for time, it gives you a feel for what you should focus on to really get ready for the final. So that hopefully that should take a little bit of pressure when it comes to studying for the final. I know the final can sometimes be intimidating because it's an entire semester's worth of work, and we've covered a lot of material in this class. That's the nature of general chemistry. We've got a lot of content to go over. So I'm hoping that study guide will make studying a little bit easier for you. Okay. The other thing you want to use are the practice finals that I've posted to Blackboard in the content section as well. These are old exams. So remember, your final is an ACS exam. Okay, that comes from the American Chemical Society. And so to help you out, I've posted a couple of old ACS exams. Now, because the ACS is, very careful about test security and things, I can't post anything very recent. So the examples I've posted are really old, decommissioned exams, and so it was okay to use them as practices. But you have to keep in mind that a lot of time has passed since those exams were used. So the curriculum changes a little bit. Sometimes just the language changes a little bit. For example, you'll notice on that first exam, practice exam, they use cubic centimeters for volumes, whereas typically you'll probably see volume written in milliliters, which is the same. The cubic centimeters and milliliters are the same thing. 1 cubic centimeter is equal to 1 milliliter, right? They're equivalent. But again, sometimes just seeing that written slightly different probably will throw you a little bit for a loop. But anyway, my point here is that you want to use these practice exams to get a feel for kind of how these questions generally are phrased, okay, and like kind of the structure of the exam. There's 60 multiple choice questions. It's just that it's the same content we've covered all semester. It's just someone else is writing the questions besides me. That's the only difference. But the content is still the same. So I recommend going through the study guide, brushing up on any topics you see on there that you feel like, oh, I haven't covered this in a while. I really should brush up on this. Try the practice exams out. I recommend having the study guide in front of you in case you get to a question that's that was part of the curriculum in the past that no longer is. Instead of spending a lot of time trying to figure it out, especially because it's something that's probably not emphasized as much anymore, and we probably didn't go into a lot of detail on it. You may want to have the study guide in front of you. And if you get to questions like that, double check that they're on the study guide, or that topic's on the study guide, because you don't want to waste too much effort there if it's something you don't have to worry about. Okay, and that's typically how I help students review for the final. Usually, students go through the study guide and look at all the topics that they need to go over, and they'll either ask me for a practice question to go over a practice question on that topic with them. Or sometimes I'll have students who are working on the practice final, and they'll reach a question that they struggle with, and again, I can help them out with that. But that's pretty much how my review sessions work. It's kind of student driven. You have to go through that study guide and the practice exams if you want to get a feel for what you need to work on, and only then can I really help you with what you need to work on. Okay, so that's my last parting piece of advice in terms of getting ready for the final. And as I said, as always, you're always welcome to discuss this with me. We can work on some practice problems to help get you ready. Okay, so good luck. Thanks for the fun semester, and go Timberwolves.